Okay, yeah, so my first announcement today is that, yeah, we don't have class Wednesday. That's, if you have classes that begin before 5 p.m., they should be canceled. And then if you meet after, I think, 5 or 5:30, those evening classes are taking place. It's Faculty Development Day, so whatever. We're supposed to, yes. Oh, I totally agree. Preaching to the choir. You're preaching to the choir. I mean, I agree. And, you know, I've been to different faculty developments over the years, and if I felt like we were getting something really, really good out of it, I would be for it, but I'm not for it. It's contact hours with students, and so, yeah, I agree with you. But I can't change the way things are, and so you have the day off. All right? Questions over homework? You can talk to me about the quiz afterward. Number 9? Yes? From 3-3, right? So I'm being asked about finding the derivative. You're given g of x equals natural log of a minus x over a plus x. And you're trying to find the derivative of this. So there's actually two different approaches you could take to this. You could just straight away go for it, and what I mean by that is you could just say the derivative is, and then you have you're saying natural log of something, right? The derivative of natural log of something is 1 over that something. So I could just put 1 over, and I will flip it, yep. I'll flip it on the next step, times now the derivative of what's inside. And remember, with the derivative of natural log of something, you don't have to put that natural log e down here, right? If it was log base 2, you'd have to put natural log 2 down here. But it's natural log. So the derivative of what's inside is going to require a quotient rule. Derivative of the top times the bottom minus derivative of the bottom times the top all over the bottom squared, right? That's a quotient rule. Now here, a is a constant. So what is the derivative of the top? Just that, no, because derivative of a is what? 0. It's a constant, so derivative of a is 0. And then derivative of negative x is negative 1. So you would get negative 1. Is that where maybe it had a problem? Times the bottom minus, what's the derivative of the bottom? X, derivative of x is 1, okay, times the top all over the bottom thing squared. Are y'all okay up to that point? Any questions there? Clean that up. I'm going to flip this first one over, a plus x over a minus x, times, let's see, this turns out to be negative a minus x minus a plus x. That's what happens when I distribute through here. So that's just negative 2a, and then a plus x squared. Just so you know, I'm expecting an important text, possibly phone call. That's why my phone just went off. And that is not what I was waiting for. You see the cancellation here? One of these cancels with one of those. So you have negative 2a over a squared minus x squared. What happened there? Yeah, I took these two things that were left on the bottom. I noticed that they were the same thing except different sign between them, so it's like a difference of squares. So I just multiplied them back together and did this. You could have left them as separate factors either way. Is that what the book had? Or something like that? That's option one. Okay, if I were doing this problem, I would not have done it that way. I would have done it by using the fact that this looks like natural log of something over something. And there's a property of logs that says that turns into natural log of u minus natural log of v. Right? Division inside of a single log turns into two different logs separated by subtraction. So I would have started the original problem by rewriting g of x as natural log of what? A minus x minus natural log of a plus x. And now I just would have differentiated these. Because there's subtraction, I would just differentiate term by term, each one. Derivative natural log of something is 1 over it, right, times the derivative of what's inside. What's the derivative of what's inside? -1, so I'd have -1 on top of what was in there. Then minus derivative natural log of this would be 1 over it, and then times the derivative of what's in there. Derivative of what's in there is +1, so it's 1 over a plus x. Yeah, that'd be it. Now you could get a common denominator, but to do that you'd have to, right, if you want to put those together, you have to introduce an a plus x top and bottom here, a minus x top and bottom here, and if you did that, you would put them together, you'd get this. I would accept that, yes. Any others? No? So the homework was fine? You weren't kidding when you said you don't like those letters in there, were you? I remember you said that, right? Okay, all right. Natural log ax plus b. Is this the one right now? Is this okay to do this one? I see chain rule because I have a linear expression sitting inside of a log, sitting inside of a tangent. So it's like inside, middle, outer. So I want to start by taking derivative of what's on the outside and working my way in using chain rule. So the derivative of tangent of something, right, here's my something. The derivative of tangent of something is secant squared of that something, the whole thing. Don't touch it. Just leave it alone. There. Then times the derivative of what was inside tangent. So forget the tangent. Now we have derivative of natural log of something, which is 1 over that something. Then, continuing chain rule, inside here is ax plus b. The derivative of ax plus b is a, right? Right? If that said 4x, the derivative would be 4. If that said 10x, it would be 10. If that said pi x, it would be pi, right? So if it's ax, it's just a. And then derivative of b is 0. So you put that a over. So just put that a on top of that, maybe slide that whole thing out in front of the secant squared, you're done. Yeah, 15. Cry, don't cry. Oh, natural log of s. Okay.
I asked a Cal 3 student how to do it. She didn't know.
Well, I don't know what to say about that. That begs the question, in Cal 3, are you going to remember any of this? You'll need it, but will you remember it? Okay, so I see composition again. I have a natural log sitting inside of a natural log. So we start with the outer natural log. So I have natural log of something right here, right? The derivative of natural log of something is 1 over that something. Now, continuing chain rule times the derivative of what's in here now, right? So what's in here, right, that is another natural log. So the derivative of a natural log of something is 1 over what was in it. So 1 over s. And then you go inside and you take the derivative of s. The derivative of s here is 1, because in this problem, s is considered, I believe, to be a variable. Does it say? Does it say? Oh, yeah, sorry, it says in the beginning. Sorry, I should have pointed this out. F of s. So yes, you can assume that s is your variable. So s is not a constant in this problem. If s had been a constant, the natural log of a number natural log of a number would all just be a number, and derivative of a number would be 0. So we're okay here. So the n here would be times derivative of s, but that's 1, because we're differentiating with respect to s, because s is our independent variable. Okay? Okay. You could do that. Yep, that'd be okay. Because this is multiplication down here. What it could not be is this, though. It could not be this. Right? Natural log of s squared. This s is trapped inside the log. This s is not inside with that s. So it needs to be out in front. All right, well, let's keep trucking along then, I guess. We stopped last time with this whole idea of logarithmic differentiation, right? We saw that there was a way to start off with something and then take the log on both sides and use properties of logs to try and make a pretty ugly derivative at least more palatable, right? Now we're going to look at something we haven't seen, but we're still going to bring in the logarithmic idea, the idea of bringing log in on both sides. So let me do a quick little refresher, recall, that if I have something like this, y equals x to the 4th, then the derivative of that is 4x to the 3rd. We used the power rule here, didn't we? And those are the types of problems we wish to see, right? We hope to see that sort of thing. We're happy when we see those. Compared to this, if I have 4 to the x instead of x to the 4, now the derivative is 4 to the x times natural log 4. That's your derivative. So that was last time. This is basically the derivative of an exponential, right? So the main differences here, variable is in the base, numbers in the exponent, versus numbers in the base, variables in the exponent, right? These two graphs look completely different. One is a polynomial, right? Curve, you know, that almost looks like a parabola. This one is an exponential function, goes up on one end, has a horizontal asymptote on the other. Clear? Yes? I plug in different values of x here. We can, right? I can plug in 1, plug in 2. You could figure out what they are, right? Plug in 1, we get 4. Plug in 2, we get 16, right? Up there, plug in 1, we get 1. Plug in 2, we get some, you know. You could plug values in. But have you ever seen this function? Probably not. This is probably the first time you've ever seen that. X to the x. Have you ever thought that maybe you could have a function that does that? Yeah, I mean, it's kind of odd. This is a pretty well-defined function as long as x is positive. Because, I mean, let's just plug in some values to get an idea of what would happen here. What happens if we plug in 1? 1 to the 1 would be 1. How about if we plug in 2? 2 to the 2 would be 4. We plug in 3. 3 to the 3 would be 27, right? 3 times 3 times 3. 4 to the 4, right? I guess the only thing would be, what if you plug in things that aren't nice integers, like nice numbers like that? Could you do maybe 1/2 to the 1/2. So you're plugging in 1/2. Isn't that just the square root of 1/2? Right? Square root of 1/2. Makes perfect sense. You can take the square root of 1/2. How about if I plug in something like 0.1 to the 0.1? Well, that would be like the 10th root of 1/10. So this makes perfect sense. What you can't do, though, is have a negative down there. So the reason why is because we don't define exponents, raising things to negative. We can raise things to a negative power. You just can't raise a negative number to a negative power. In general, you can't. So as long as the x is positive, we're pretty good. All right? Bring out good old faithful graphing program here. Let's see how it handles x raised to the x. Hey, I mean, there's a graph, right? Doesn't look like anything happens over here with negative values, but there is a graph over there. And since there's graph, there should be tangent line, shouldn't there? So the question is, what's the derivative of that, right? What's the derivative? And if we want to know the derivative, then we get confused. I hope you get confused, because one part of you is saying, if I have x down here, I bring that thing down and subtract 1, and you do that. If what's down here is the variable and what's up here is a number, well, I have a variable down here, but variables up here also. So maybe you're thinking you want to do it this way, right? Or maybe you want to do some weird, crazy version of both, right? Where like you do the power and the log all at the same time. It turns out you do neither one. This is just a very special case where your base is some function of x, right? It's a function of x. And your exponent is some other function of x. Now, in this particular problem, they're the same function. But it would be perfectly fine if I made this maybe x, and up there made that like x squared plus 2. If what's down on the bottom and what's up on the top both are determined by a function of x, then we need to figure out a way of handling the derivative. All right, so here we go. This is how we do it. Start a new page. So here's an example. Everyone understand what I'm trying to do, though? Like, get an idea of what's going on? Okay. I want us to find y prime. So we start off by just writing the equation down. And we did the same thing when we employed the logarithmic differentiation. Is if we're going to come in with log, you have to come in on both sides of the equation with log. So we need to start with an equation. So there's our equation. I take the natural log on both sides. And now what? That's right. There's a property of logs that says that this power x can come out in front. Now, in the past, the property that we wrote down, I think we wrote it last class also, was that this was like x to the n, and then the n came out. But if it's x to the x, well, whatever the power is still drops out. So what we get is this. Natural log y equals x times natural log x. At this point, I'm ready to roll because I can do implicit differentiation on both sides. The derivative of natural log of y, we did that last class. Here I'm going to use what? Take the derivative there. Product rule, right? That's a product, isn't it? I'm going to take derivative of a product, so I'm just going to apply the product rule. So what we get is this. What is the derivative of natural log of y? Be careful. 1 over y times y prime. That's chain rule, isn't it? Derivative of natural log of y is 1 over y prime. Now the derivative of the right side. I should put my little squiggly so you know I'm differentiating. So derivative of x is 1 times natural log x, right? Plus, what's derivative of natural log x? 1 over x. Now finish off the product rule times x, right? Everyone see product rule here? Was it that good of a weekend? Y'all okay? Product rule. This is f, this is g. The derivative of f times g is f prime g plus g prime f. Did that help? No? Yes? Okay. Everyone else okay? What is this then? That's just 1, and the other one, natural log x. So we get that 1 over y prime, equals just natural log x plus 1. We're trying to figure out what y prime is, right? I have a 1 over y here. So remember what we did with that last time? Logarithmic differentiation? We multiply both sides by y, didn't we? So I get y prime equals, I'm just going to put the y in front, y natural log x plus 1. By y. Sorry. My wife packed me lunch today. I'm like, I feel like I'm in grade school again. I'm not ungrateful. I'm just not ready for that today. All right. So that's what y prime is. Now, the problem with this is that our derivative has y in it. We'd like for it to just be in terms of x. We just go back to the very beginning. What was y? Y was x to the x. So replace this here with x to the x. So the derivative is x to the x times natural log x plus 1. So let me show you something. If we wanted to find the slope of the tangent line to the curve x to the x at x equals 2, what's the slope of the tangent line? So at x equals 2, the slope of the tangent line to that curve should be 2 to the 2 natural log 2 plus 1, right? That's just, this is the derivative. This is the slope of tangent line at a particular value of x. If I say what's happening at 2, you come in here 2 to the 2, and then I need my calculator, which you're already firing away there. Natural log of 2 is going to be a decimal, and then add 1 to it, and then times what? 2 to the 2 is 4, so 6.77? Approximately 6.77. So I'm going to go back to that graph I had here. And if I try and go out to 2, that's not what I want. I'm going to go to an x value of 2. See, this is the tangent line right there. The slope of it, whoa, something ain't right. Oh, I'm at 2.2. Thank you. I thought it had changed that. Come on. There. At 2, right, we're here, the slope is 6.77. Make sense? So it's all the same game. I mean, we're doing the same thing we've been doing since almost the very beginning. We're trying to find slopes of tangent lines. That's what the derivative gives us. It's just that what we're actually finding the slope of, the tangent line, the function itself, is becoming more and more complicated. We good? Let me try a different one. How about all right, let's try this. How about tangent x raised to the 1 over x? This is probably going to be just a nutty looking thing. Yeah. So this is a function. Its tangent of x raised to the 1 over x. And so we know that tangent's undefined some places because tangent has these weird asymptotes in it. And then raising it to the 1 over x, we know we can't plug in 0 because we get division by 0. And there's all sorts of craziness happening, which is why this graph does something and all of a sudden stops and then does something and stops. And, it's got these breaks in it. So there's lots of issues with domain. But where it's defined, there are slopes of tangent lines in different places. So we need to try and come up with a formula that would give us the slopes. All right? So let's do that. So let's let y be equal to tangent x raised to the 1 over x. So what's going to tip you off that you need to use logarithmic differentiation? 1 over x? Because you have an x up there, is that what you're saying in the exponent? Yes? But there's an x also in the base, right? If you just had this, right? If I had like pi raised to the 1 over x, would I use logarithmic differentiation? No, this is like an a to the x. This you would use exponential. So the derivative of this would not be, you would not employ this method because the base doesn't have x in it. Understand? So it's the fact that I see the base and the exponent both have x's that I am going to think logarithmic differentiation. So I come in here on both sides, I take the natural log. Why do we use natural log and not some other log? Because when we differentiate, the derivative of natural log is real clean, right? So that's why we use that one. All right, by doing that, I'll be able to drop down the 1 over x in front. And then I'll have times natural log tangent to x. We agree? Now, derivative, implicit, differentiation. Derivative left side is always going to be what? 1 over y prime. All right, that's not going to change. That's good news. Now, on the right side, I have some choices to make here. I could look at this as product rule, couldn't I? Could I have also just put the x underneath this whole thing and just done a quotient rule on that side? What would you have done? Product? You would have stuck with product? Okay. Now, the derivative of 1 over x, you have to remember 1 over x is x to the negative 1. So the derivative is negative x to the negative 2, which is negative 1 over x squared. Right? I'm just saying you could get this by yourself, like this is not going to be a trip up, hopefully. Negative 1 over x squared is a derivative of 1 over x times natural log tan x. Finishing off product rule, what's the derivative of natural log of something? 1 over what's inside of it, right? Then what was the derivative of tangent? Secant squared x. So I'm done. This right here is the derivative of natural log of tan x right here. Then finish off product rule, what still needs to be out here? Times 1 over x. That's a pretty ugly looking thing. Negative natural log tan x over x squared. The other one, let me see, I still have a plus. It's secant squared x over x tan x. And that's just 1 over y prime, right? 1 over y prime y? 1 over y prime. That's what that is, right? So I'm going to have to always put that y on the other side. That's going to happen every single time. So I'm going to have y prime here. I'm going to bring the y in on both sides. But what was y? Yes, tan x to the 1 over x. Do y'all see my y? I just tacked it on the end. Just make sure you put all this in parentheses if you're going to do that. see if that's the text I've been waiting for. Yes, that's it. Let me just check this real quick. I apologize. Okay. Good, good. Any questions? I'm not going to clean that up anymore. I'm done. Just finished. Pardon? I don't know. I mean, probably. I brought it up only because that's what I initially wanted to do. The only reason I didn't wind up doing quotient rules because when I wrote it down here, when I had already decided to take derivative, it was kind of too late to rewrite that, so I just went with product rule. This right here? Remember this 1 over y right here is always going to be there? Who's asking? Okay. Remember, the derivative of natural log y is always going to be 1 over y prime. So you're always going to need to multiply both sides by y to get it out of there? Yes? So I multiplied this side by y, it went away, and then on this side, I multiplied by y. This is y. This, if you go back to the very beginning, y was equal to tan x raised to the 1 over x, right? So that's y right there. Clear? Okay. All right, that's it. Now, we're not going to go and try any points in there or anything like that, but you could. This reminds me of this problem someone asked one time. X to the x to the x forever is equal to 2. Solve for x. So what number, when you raise it to itself, to itself, to itself, to itself, to itself forever, will equal 2? Well, we have to first agree that if this equation has a solution, that this is true then, right? I mean, if there is an answer, the assumption is that that's true. Yes? If there's an answer, then that has to be true. Okay, what I'm going to do is I'm going to take natural log on both sides. And then I'm going to look at the x to the x to the x to the x to the x forever, right? Just this one, though. Just leave this one here. Just that first one all the way up, right, is what? X to the x to the x. Bring that out, right? So this is x to the x to the x forever. Natural log x must equal natural log 2. And now, what did we say that if this equation is true, what does this have to be equal to? That has to be equal to 2, right, if this is going to be true. So that has to be 2. The fact that there's infinitely many of them means that me peeling off just one of them doesn't change anything because it's infinite. Right? If I say go to infinity and then -1 or something, it's not going to change the fact that you're going to infinity. So 2 natural log x equals natural log 2. And what am I trying to solve for here? Trying to solve for x, right? What is x going to be? So what I can do now, there's several ways to look at this. I can use this property. I can pop that thing back up there, make it natural log x squared equals natural log 2. And then I can come in, I can do e on both sides, the inverse. What happens when you put e and natural log together? They cancel out, and so I just get x squared over here, and over here I get what? E net just 2, and then solve that, you get x is what? Plus or minus root 2, but I'll only look at the positive one, root 2. So if you were able to do it, which you can't do it, you can't check this answer, but root 2 to the root 2 to the root 2 to the root 2 to the root 2 forever, you would get 2. What you could do on your calculator is go out, a little bit. You could do like maybe 10 of them, and you should get close to 2. Just a weird little application of that. When I was in school or just finishing up school, there were like a group of people they would always like throw problems at each other, see if we could stump each other. Like these. I remember someone gave me this one. There was another one. What's that? How to what? Well, because that's what I'm That's what I'm trying to find what x makes this true, right? So whatever x makes this true would mean that this would have to turn into 2, right? I mean, this is going to have to be equal to 2 if this what's that? It would be, well, again, it goes back to the idea that this goes forever. So by me pulling just this part of it off and peeling that out front, does that really change the fact that there's infinitely many? It just keeps going forever. So we can get into like an argument about this. I mean, like, I understand that it's not easy to just look at that and be like, yes, I agree with that. But let's not get into that because we have to talk too much about going to infinity and whether or not peeling off one term really makes a difference. And you do that a lot in Cal 2. You actually will study that more. But I was just trying to show you an example of how that natural log property just pops up everywhere. It's like all these different places, you just have to know it. You can work with it. I'm going off on a tangent, so I'm going to just get back to work. All right. God, what a great problem. Find y prime if x to the y equals y to the x. All right, so now I need to remind you of when we first started implicit differentiation. It's when we had an equation where we couldn't solve for x or we couldn't solve for y and we couldn't isolate the variable, so we used implicit differentiation. That's what we did. Here we want to do the same sort of thing because I can't solve for x exactly because it's on both sides. I can't solve for y exactly, it's on both sides. So I want to do implicit differentiation. The problem is, what's the derivative of x to the y? Well, what did we do when we were trying to do something like this just a second ago? We pulled the power out, right? With the log. And so I think I'm going to need to come in and initially just do log on both sides and see what happens. So I'm taking natural log of the left side and take natural log of the right side. That allows me to drop out the powers. So I get y natural log x equals x natural log y. Do you agree with that? That's a new equation. And now can I take the derivative of this? Yes. So I'm going to do implicit differentiation. That means derivative on left side and right side. I'm treating x like my independent variable and y like my dependent one. In other words, I'm going to treat this like this. dy dx is y prime. Anywhere I take derivative of x, I will get what? Derivative of x, I'll get 1, right? And anytime I take derivative of y, I'll get y prime. Okay. So let's do the left side. I'm going to use product rule here, right? What's the derivative of y? Y prime times natural log x, and then more product rule plus derivative of natural log of x, 1 over x, right? Finish off product rule times y. Everyone see that's product rule on the left side? Equals. Same thing on the right side, except we have a different product, right? This time the x is out front, the y is on the natural log. So derivative of x is 1 times natural log y plus, careful, 1 over y prime, good, times, finish off product rule, x. Good, good. Did y'all see all that? We had the product rule again on the right side. Derivative of x, natural log y, plus derivative of natural log y times x. And now it's just a matter of getting all your y primes by themselves. Y'all hated this when we did this in the past. You want to get all the terms that have y primes, so this one and this whole thing right here. Get both of those together on one side of the equation. Everything that, man, those colors come out great on this projector, don't they? I really like that highlight on there. All right. Move this to the right, move that one over here. So y prime ln x minus x over y prime equals ln y minus y over x. Now I did kind of put some of the fractions together, right? 1 over x times y is y over x. Moved it to the other side, that's this. On this one on the right, I put the x on top of the y, and I left the y prime out because I'm going to factor it out anyway. So I put this x over y, and then I brought it over here, which made it negative. And then I factor the y primes out on the left. So y prime comes out. What am I left with? ln x minus x over y equals ln y minus y over x. We're almost there, right? Almost there. Just going to divide through by this thing right there. And that's my derivative. Now in this problem, I don't have to replace my y like I did in the previous problem. The reason why is because I can't solve for y. If I could have solved for y in the very beginning of the problem, I probably would have used a different type of differentiation. But the fact that I couldn't get y by itself means that I'm never going to be able to come back here and replace these y's with anything. Not easily. Do y'all see what I'm saying? So we're done at this point. Any questions? Okay, last time I signed up through what problem here? What did I give you through? 1 through 25? More than that? Yeah, no, that sounds about right, actually. Okay. So what I think you should look at now is page 170. I think you should look at 45. I didn't give you out of the 50s? Okay. All right. That's what I thought. So now what you can do is 56 through 60. '62 and 63. Okay, 56 through 60 are like the ones we did here, like x to the x, tangent x to the 1 over x. I really like putting problems like that on the test. So make sure you cover all that. That's why I let you do the evens in there also. All right. That's it. That's it for that section. We're done. Huh? That's it for today? Is that what? Oh. See? You're crazy. I'll let you go a little early today, but not crazy early. So next on our schedule is 3.5, and it's inverse trig functions and their derivatives, and then we can get into hyperbolic trig functions and their derivatives, which I think is all fine and great and whatever. I'm actually going to skip them. I'm not skipping them. I'm going to do them, but I'm doing them after I do 3.7. I want to do 3.7 first because I'm just so excited to show it to you. I think you're going to be happy about it. This is the only time we're meeting this week, and so I think that, you know, give you something to Yeah, we don't meet on Wednesday. So
I try to watch these videos in order, and if I drive,
I know.
dates, and I
I
got.
understand. I'm sorry, but it's better. You're better served by watching them than you would be if you didn't. So, and they're always there to go back to. So 3.7 should be pretty clean. Like no one has probably looked at it. Maybe some of you looked ahead. But this is one of the best results that happens in calculus. Okay. This is a big deal. All right. This section, it's used a lot. It comes up in Cal 2 all over the place. In Cal 3, it comes up. And it's known as L'Hopital's rule. Now, L'Hopital's rule, it's pronounced L'Hopital, but it's spelled like La Hospital. All right? I'm not sure if that's even how you spell hospitals, but that's the way it looks to me, hospitals. L'Hopital. And L'Hopital's rule is one of the best, most useful things that I can think of when it comes to calculus. I mean, it is a great tool. So here's how it works, okay? And if you have something, let's go back to something like this. Limit, you thought the limit was over, didn't you? Hold on, though. Hold on. Limit x equals, x goes to 2 of x squared minus 4 over x minus 2. Now remember that stuff? We said what happens as x goes to 2 here? So the first thing you were supposed to do is just a direct evaluation. You're just try and plug 2 in and see what happens. So let's plug 2 in and what do you get? So on top we get 0. On the bottom we get 0. This is what we call the form of the limit. Do you remember me saying that was our form? Yes? The form of this limit is 0 over 0. If you ever have a limit that has the form 0 over 0, you can always apply L'Hopital's rule. Okay? Always. Now, I'm going to show you L'Hopital's rule, but not yet. I want to show you another form that you're allowed to use L'Hopital's rule on. Limit x goes to infinity. We'll go x squared minus x over 3x squared plus x. I said x squared minus x. I meant to say x squared minus 1. X squared minus 1, 3x squared plus x. What? And I'm letting x go where? Infinity. This is infinity over infinity, right? That is the form that we have here. You are allowed to apply L'Hopital's rule whenever this happens also. These two forms are good for L'Hopital's rule. Both of these forms fall into a group of forms called indeterminate forms. They're things that we know something's happening. We know the top's going to 0. We know the bottom's going to 0 in the first one. Second one, we know the top's going to infinity, bottom's going to infinity. We've seen that they could go to a number, though, right? It could turn out to be like the top one may turn out to be, 4 or something. And the bottom one may turn out to be like 1/3. This right here is not enough for us to nail down the answer, right? So it's indeterminate, meaning we're not quite sure how to determine the answer. So these fall into the group called indeterminate forms. Now there is a whole slew of indeterminate forms. This is just 2 of them. But these are the only 2 that you can use L'Hopital's rule on. All right? So the rest of today is going to be me showing you how to use L'Hopital's rule, and then me showing you the other indeterminate forms, and showing how you can take even the other indeterminate forms that don't look like this, and you can always turn them into these. And then L'Hopital's rule just becomes the shit. I mean, I don't know if there's another way to describe it. It is, I don't know, I mean, that to me makes it's a good description of it. If you don't know L'Hopital's rule, then you're really missing out on, you'll see. You're going to be pissed at me. Watch. You're going to be really mad in a second when I show you this rule. You're going to wonder why I didn't show this to you already. Okay, so let me give you the rule. It's real simple. If you take a limit, and it doesn't really even matter what the heck it is down here. It doesn't matter what's going on there, all right? But you got some function on top, f, on something on the bottom, g, all right? So you got like a numerator and denominator, right? If this limit is going to the form 0 over 0 or infinity over infinity, okay, either way. And by the way, it doesn't matter if it's plus or minus on the infinities. It's just if the top's going big, bottom's going big. So I'm going to put here plus or minus next to those because I don't want you to be like, well, wait, the top was going to negative infinity, so I didn't know if I could use the rule. Doesn't matter. As long as these are both becoming infinite, regardless of sign, you can use the rule. So the rule says if you're getting one of those two forms, right? That's what it's saying. Then that limit that you're trying to find, okay, that's the limit you're trying to find, will be equal to the limit of this. So what is that saying? If you're trying to find a limit and you're having trouble because you're getting 0 over 0 or infinity over infinity, instead of looking at f divided by g, look at what? The derivative of f divided by the derivative of g. This is not a quotient rule, right? This is one of the rare times ever you're allowed to just do derivative on top and bottom separately. Whatever this answer is the answer to what you're trying to find. So now let's go revisit a problem. Example, I'll go to a new page. Find the limit as x goes to 2 of x squared minus 4 over x minus 2. Does anybody know how to do this, remember how to do this without doing L'Hopital's rule? I mean, what would you have to do without L'Hopital? You'd break apart top. So I'm going to do it on the side. You don't need to write this down, but I want us to remember what we had to do. We'd have to factor the top to be x plus 2, x minus 2. So we had to recognize the difference of squares, didn't we? Then over x plus or x minus 2 on the bottom. Then we canceled the factors. And then we just direct substitution 2 in there. Sorry. Direct substitution in there at this point, right? And you get what? 2 plus 2, which is 4. That's the way we did it in the very beginning. And then we learned that, you know what, these limits get real ugly because the algebra in there gets crazy, and right? Now let's use L'Hopital's rule. What is the form of this? We already said it was 0 over 0, right? So this limit is equal to a new limit. This new limit still x goes to 2, but now instead of doing x squared minus 4 on top and x minus 2 on bottom, I'm going to do the derivative of the top and the derivative of the bottom. What's derivative of the top? 2x. What's the derivative of the bottom? 1. Now plug in 2. And what do you get? 4. Okay. Do you all see that rule? Do you see how I applied that? Now, I used L'Hopital's rule from here to here, didn't I? So we have to let people know that we use the rule. So there's two ways. The books usually put an H right here for like L'Hopital's the L with the apostrophe H, right? Some books will put an H and they'll circle it. I've always just put an L and circled it. I don't care what you do. But you need to let someone know you use the rule. So by L'Hopital's rule, you have this. Wow, that's pretty nice, right? New page, new example. Limit, let's go, theta goes to 0, tan 4 theta over sine 3 theta. You remember this one? I don't know if you remember how we did this. We like had to peel it apart, rewrite sine 4 theta as, tangent 4 theta as sine 4 theta over cosine 4 theta, and then peel it all apart and then try and imagine that we were trying to make one of them go to that, use that special thing and make it go to 1, and had to like make things appear and then move it around. Do y'all remember all that crap? Okay. But really now, if we just, let direct substitution, we do get 0 over 0. Right? Tangent of 0, 0, sine of 0, 0. So that does apply. You can apply L'Hopital's rule to this. So by L'Hopital's rule, we take the derivative of tangent of 4 theta, which is secant squared 4 theta times 4. Good. Chain rule. Don't forget, you still have to take the derivative, right? And then over what? What's derivative of sine of 3 theta? Cosine 3 theta times 3. Again, chain rule, having taken derivative of 3 theta. Questions on that? Okay, let theta go to 0 now. 0, secant of 0 is the same as 1 over cosine of 0. Cosine of 0 is 1. So secant of 0 is 1. Squared is 1. 1 times 4 is 4. Cosine of 0, we said just now, was 1. 1 times 3 is 3. So the answer is 4/3. And we're done. You're just slamming your pen. Why are you getting mad? Everyone gets mad, I understand. But let's talk about it, because do you really have a right to be mad? Think about this for a second. Think about your argument. Who wants to be the one who tells me why I couldn't show you this? What do you have to do in order to do this? You have to be able to take a derivative, right? We learned limits before we learned derivatives. In fact, the derivative is a limit, isn't it? The derivative is a limit as h goes to 0 of f of x plus h minus f of x all over h, right? That's the derivative. So it's kind of like you wanted me to come in here and start teaching you limits and then say, when you get to something like this, take a derivative, but you have no idea what a derivative is, do you? See what I'm saying? It's like you can't get the carriage in front of the horse. You cannot, I could not show you this because you did not know the derivative. Now, what we're doing is we're using the derivative to come back and look at limits again and go, oh, wow, we can do those limits a lot easier now using the derivative. So that's why you didn't see it. I know I felt robbed too when I first, when it first was shown to me. I was like, wait a minute, man, why did we do all that crap? And then, oh, okay, yeah, well, I couldn't have done that. How are you going to do chain rule? You don't even know chain rule at this point. Okay. I had at some point early in my academic career, I picked up a Cliff Notes on calculus, like thinking I could learn calculus in Cliff Notes. And I remember just reading through it, and it's like when they took a derivative like tangent 4 theta turned into this, and I hadn't taken a calculus class. I had no idea what chain rule was. I had no idea. All I knew was like basic arithmetic, addition, subtraction, multiplication, division. Like I didn't understand what a derivative was. So to me, it was like total voodoo-ness. Like it didn't make any sense how tangent could turn into this. I'm sitting there trying to figure out like what they did. Like did they multiply? Did they flip something? Algebraically, there's no explanation for a derivative, right? So it's kind of like if I would have come in here and said, just do this to it, you'd have been like, what the hell are you doing, man? It doesn't make any sense. So now I hope that kind of resolves it. You're not so upset. You still upset? Okay, now this is going to open up a huge window for us as far as what we can actually find derivatives or take limits of. We can do a lot of limits now that are pretty complicated. That could be potentially very complicated. Let's look at this one. Limit x goes to 1 of natural log x over x minus 1. Now, there's just nothing you would be able to do with this at all without L'Hopital's rule. Like you wouldn't be able to handle this because there's no algebraic way you can figure this out. Like there's nothing, there's no factoring, there's no come in with this conjugate or I mean you'd just be stuck. But it has the appropriate form because what's natural log of 1? Just doing direct substitution. Natural log of 1 is 0. I'll help you out. And then 1 minus 1 is 0. So you get 0 over 0. That's the appropriate form for L'Hopital's rule. So apply it. L'Hopital, limit x goes to 1. And then, what is the derivative of the top? 1 over x. What is the derivative of the bottom? 1. So it's just 1. So you get x go to 1 now, you just get 1 over 1, and you're done. Isn't it great? Pardon? On this problem? Oh. Oh yeah, as long as it's infinity over infinity, you can use L'Hopital. I haven't done one of those, have I? Let me take you back to one of our favorites. How about this one? Remember that one? I gave that quiz very beginning of class. I was like, there were 2 formulas everyone had to know. Go ahead and write them down. And right, it was like very beginning semester, right? And then like 1 person knew it or something out of everyone in the class. But what is it now? What's it supposed to be? I mean, 1, right? That's 1. You're supposed to memorize that, right? But let's now think about it like why it's 1. So what's the form? Plug in sine of 0 is 0, and then 0 on the bottom, 0, and so you have the kind of form that you need for L'Hopital. According to L'Hopital, this is a new limit, except you do derivative of the top, which is cosine x, over the derivative of the bottom, which is 1. And then cosine of 0 is 1, 1 over 1 is 1. We good? Yeah? Okay. How about this? I'm thinking, hold on. There you go. X is going to infinity, x cubed over e to the x. So what does x cubed do as you go to infinity? It goes to infinity, right? So you have infinity on top. On the bottom, what does e to the x do? Remember, e to the x is an exponential function. As you go out to infinity, it takes off to infinity. Remember last class I said we need to know what those look like. So as we go to infinity, it goes to infinity. So we have infinity over infinity. This is the appropriate form that we need for L'Hopital. But now I need derivatives. So what is the derivative of x cubed? 3x squared. What is the derivative of e to the x? Itself, e to the x. And that's it, right? You know what gets real, not frustrating, but like kind of disappointing? It's like, when I'm grading a test and someone's here and they use L'Hopital's rule, right? And guess what they do here instead of just derivative top and bottom? They do quotient rule. It's like all semester they've been trying to figure out the quotient rule, trying to get it right. They finally got the quotient rule right, and they do it in the wrong place. They do it on L'Hopital. L'Hopital, you don't use quotient rule. It's just derivative top and bottom. And so I see it, I'm like, oh. 1 point, yeah. Now what? Let x go to infinity again? You still have infinity over infinity, don't you? Well, then that didn't help, did it? But the great thing about things like this in math is if something, works, try and do it again, right? It's almost like I walked in and that's my brand new problem. No one told me that came from something else, right? So just apply L'Hopital's rule second time. Do L'Hopital on that. What would you get if you did L'Hopital on that? This time you get, what, 6x over e to the x? And still, but what's happening though? You're losing powers on the top. Eventually, right, that power on top is going to go to a constant. So we're still at infinity over infinity. So finally, L'Hopital one more time. Limit x goes to infinity of 6 over e to the x. Now what's happening as x goes to infinity? You have fixed over infinity. Fixed over infinity goes to fixed over infinity goes to, my little math heart is crying right now. Fixed over infinity goes to 1, goes to 0. You had an infinite number of numbers to choose from, but just think about it, okay? Don't try and memorize these things. Think about them. What happens when you have a number that's staying where it is and the number on the bottom is getting huge? That gets small, right? Okay? Now, you have to be a little careful, because notice that I actually took this limit and I got an answer, right? Could I have done L'Hopital's rule another time? No, because I do not have, in this case, infinity over infinity, do I? I have fixed over infinity. That's not L'Hopital's rule. Sometimes what people will do is they'll just try and beat the hell out of the problem with L'Hopital's rule. They'll just keep on L'Hopital ruling it, and you cannot do it unless you have 0 over 0, infinity over infinity. I'll show you a perfect example of it. If you have something like limit x goes to infinity of, let's just do x squared plus 1 over 2x squared plus 1. What form do I have? Infinity over infinity. So let's do L'Hopital once. What do you get? 2x over 4x, right? Agreed? Should I do L'Hopital again? Yeah, but don't those x's cancel? And you just get 1/2, right? And the limit of a constant is just the constant. So your answer is 1/2 here. But let's just say you got all gung-ho and you went and you did, L'Hopital again. In this problem you do, but you would get 2 over 4, right? If you did L'Hopital again. But this would be an illegal move. You couldn't do that. Right? Derivative of top would be 2, derivative of bottom would be 4. This is where we stop. We cancel, and then we get 1/2. That wasn't a very good example. It would have been better had I thrown some other stuff out here so that it would have forced you to go one more step. But it's all right. I think you understand the point. You're always looking for 0 over 0 or infinity over infinity. You cannot proceed unless you have that. Now, sometimes the algebra in these can get kind of messy. Let's talk a little bit about other indeterminate forms. So far, here's what we have. 0 over 0, infinity over infinity. Anytime we have a limit and we get one of those two, we're happy, right? We're actually happy now because we know we have L'Hopital's rule. So we know that those two are things we can't figure out unless we can somehow algebraically or with L'Hopital's rule determine the answer. But there are other things that could happen that we don't know what happens. Here they are. How about if you have infinity minus infinity? We've had that before. Do you remember that? Do you remember ever seeing that type? If you'd like, I can give you an example next to it. Limit x goes to infinity, x minus the square root of x. Anyone remember how we would do this? Factor something out? Like factor square root of x out of this. Turn it into a product. So if you were to work with that one, you would have rewritten it. I know it's been a while, okay? That's the way you would have rewritten it. You would have factored out a square root of x out of both of these. And then you have what? Infinity times infinity. Is that an indeterminate form? Infinity times infinity? That is not an indeterminate form. Because if I have something that's really, really big times something that's really, really big, the answer is something really, really big. So that's not. This is indeterminate. You got to work with it. This is not. Are we okay on this? All right, so that's indeterminate. What about this? Another indeterminate form. How about 0 times infinity? Now, remember, this is a form. I'm saying something's getting very small times something that's getting very big. I'm not saying 0 times infinity like 0 the number. Something very small, something very big. That you can't tell me what's happening because I don't know how small this one is. I don't know how fast it's getting small. I don't know how big this one is. I don't know how fast it's getting big. So I have to somehow try and figure out what's going on, right? So this is an indeterminate form. This one, these two. How about this? Do you want an example of that one? Sure, okay. An example of that one would be limit x goes to infinity. Let's go to 0. X goes to 0 from the right of x ln x. That's a good one. I like that one. Look, x goes to 0. This one goes to 0, right? Natural log of x. What does the natural log function do as you approach 0 from the right? Here's natural log x. We did this last class. This is what natural log of x looked like, right? That was an asymptote there. So what happens as you approach if you're on natural log of x, what happens as you approach 0 from the right? It goes to negative infinity, right? So this is 0 times negative infinity. That is an indeterminate form. You don't know which one gets smaller or bigger faster. Does that make sense? I'm not showing you how we're going to do this yet. I'm just showing you what types of things we're going to run into that we need to be able to handle now. What else? Here's something. What about 0 to the 0? Crap, we haven't seen that before. You've been told before that any number raised to the 0 is what? 1. But also 0 raised to any power should be 0, right? Right? If I say, what's 0 to the 5th power? You'd say 0. If I say, what's 5 raised to the 0? You'd say 1. So what's happening here is there's two things that are kind of like arguing with each other. This exponent is saying, hey, look, no matter what you are, I want to turn you into a 1. And then the base is saying, hey, I don't care about you. I just want to be 0. And so as each one of them is trying to get to where they want to go, they're battling each other. And so you try and figure out who wins, right? That's an indeterminate form. Here's an example of that. Limit x goes to 0, sine x raised to the x. If I let x go to 0, the base wants to be 0 and the exponent wants to be 0. So what's that going to be? Well, we'll figure it out. Then we'll have ways of doing all of these. I'm just trying to get you to see all the indeterminate forms. How about this one? You tell me if this is a problem or not. Because what happens is people start thinking that indeterminate forms are just any time you have like 0 and infinity all together. And then they're like, it's indeterminate form. But what about this? What does the base want to be? It wants to get smaller, right? It's like, I'm trying to get small, I'm trying to get small, I'm trying to get small. And the exponent is doing what? Raising it to a huge power, right? When you raise things to powers, do they get bigger? Sometimes, right? What if the number is a decimal? Like, or we'll say a fraction. What if I take 1/2? What happens if I square 1/2? Does it get bigger or smaller? Smaller. What if I take 1/3 and I raise it to the 10th? It gets smaller, right? So what's happening here is this right here is trying to get small, right? And this one right here is saying, I'm going to actually raise you to a huge power, which is going to make you multiply times yourself many times, which is going to make you even smaller than you started, right? Does that make sense? So these guys are like friends. They're like, I want to be 0. And this guy's like, I'm going to help you get there faster. And so this is not an indeterminate form. That goes to 0, and it's done. You understand? Yay or nay? Yeah. So scrap that one. Or just put on the side, that's not an indeterminate form. How about this one? 1 to the infinity. Now remember, this number is not 1. It's getting closer to 1, right? And this one is not infinity, it's getting closer. And let's do this. Let's make sure that we are clear that the number here is approaching 1 from the left. In other words, this number in here wants to get closer to 1, but it's always a little bit smaller than 1. So like maybe it's like 0.99999. Is that an indeterminate form? What does this one want to be? I want to be 1, right? Please, can I be 1? I'm getting closer and closer to 1, but I'm a little bit smaller than 1. And this guy's over here saying, well, I'm going to keep raising you to more power, so I'm going to make you multiply times yourself, right? That's not a good thing for 1, because this 1 is actually smaller than 1. We just said that if your number is smaller than 1 and you raise it to a power, it actually gets smaller, right? So this guy's trying to be 1. This asshole's over here saying what? No, you got to go back to 0, right? You see what I'm saying? I mean, this is number sense type stuff. This is what calculus, a lot of it is about. Understanding, when I've always said like fixed over infinity and all this, it's not about like memorizing stuff. It's about understanding the way the numbers work and how they behave with each other. So these two are not friends, and so it's an indeterminate form. Yes? Let me give you an example of this one. I brought my potty mouth today. Let's see. Let's make x go to somewhere interesting. How about 3? And let's go from the right. And let's go 3. So I'm bigger than 3. So how about... Boy, this became a little more complicated than I wanted it to be, but yeah, that's a lot more complicated than I wanted it to be. But so where does the base want to be? 4 minus 3 is 1, and then I have what? 1 over 3 minus 3 is 0. 1 over 0. Fixed over 0 should be like infinity, negative infinity, or does not exist. And in this case, it turns out to be positive infinity. So again, we would have to investigate this, but I'm just giving you an idea of one that would do that. What would probably have been more interesting is if I did something like, I don't know, like sine of 0 here, or cosine of 0 here, and then something else. All right, let's look at another possible indeterminate form. We said 0 to the 0. We said 1 to the infinity. How about this one? Infinity to the 0. It's about time someone beats up on infinity a little bit here. So the base is like, I want to be big, right? And the exponent's like, well, hold on, right? Hold on. I want you to be 1. And so they don't get along, do they? So that's definitely an indeterminate form. Example of this, limit x goes to, let me go to infinity to make this easy, x to the 1 over x. That's a clean one. The base wants to get big. 1 over infinity goes to 0. So you get infinity raised to the 0. Can anyone think of a different indeterminate form? Another one? Some combination of this? What do we have so far? We have 0 over 0, infinity over infinity. We have infinity minus infinity. We got 0 times infinity. We got 0 to the 0, 1 to the infinity, infinity to the 0. Am I missing anything? Negative infinity to the infinity. Well, I think you would have to look at it like that because we can't raise negative numbers to fractional powers. So that right there would still be infinite. It would be negative infinity, but it would be. So that one would not be an indeterminate form. We got 0 to the 0, right? Okay, so you ready to we'll just do one more example. I'll cut you out a little bit early today, but let's do an example of an indeterminate product. So I want to give you something where it's like 0 times infinity, something like that, and then from this we'll be able to do others later. So how about this one? Example, find the limit as x goes to 0. Let's do this one. X, 0 from the right, x natural log x. So we had this one earlier, didn't we? Notice I'm going from 0 to from the right side. Why am I doing it from the right side? Why am I specifying that? Because natural log is not defined for negative numbers, right? So I can't come in from the left side. So tell me where this goes. What's your form? This right here, x is 0, right? That's going to 0 times, and we said natural log of 0 is headed where? Natural log of 0? Negative infinity, right? Natural log of 0 is undefined. But as you get closer and closer to 0 from the right side, the natural log dips down. You have to remember that, right? Last class? Natural log dips down. So that's going to go to negative infinity. This is an indeterminate form, isn't it? Something wants to get small, something wants to get huge, but negative. Since it's an indeterminate form, we would like to bring out L'Hopital's rule. But we can't, right? Because L'Hopital only works when you have what? 0 over 0 or infinity over infinity. So I need to convert this into one of those forms. And here's where we get a little bit clever with our algebra. I'm just going to rewrite the problem. And you just tell me if you think I've broken some rule. Can I rewrite this as natural log of x over 1 over x? Isn't that the same exact problem? Because putting an x up here is the same as putting 1 over x down here. Because that would really flip back up and go up there. And you might be saying to yourself, well, why would you do that? I mean, because you seem like you're kind of making it harder than it has to be, maybe. Well, I'm using the fact that in order to do L'Hopital's rule, I have to have something 0 over 0 or infinity over infinity. By doing this, I should be able to get it. Tell me what happens as x goes to 0 here. We've already talked about it. Where does it go? Negative infinity, right? Now, look at this, though. This is different than just x, isn't it? That's 1 over x. So if x goes to 0, and x is a positive number, right, because it's bigger than 0, then I have a fixed number over 0, which should get, or fixed number over a very tiny positive number, which should explode, right? It should get infinite. So this right here, 1 over 0 goes to infinity. So my denominator now is infinite. And now don't I have infinity over infinity? See it? And I'm pretty pleased about that. Because I can apply L'Hopital's rule now. This equals, by L'Hopital's rule, the derivative of the top. What is the derivative of natural log x? 1 over x. Now very carefully, not to mess ourselves up here, what is the derivative of 1 over x? Negative 1 over x squared. Right? Negative 1 over x squared. So you have to rewrite that as what? X to the negative 1? Then bring the negative 1 out. This right here is x to the negative 1. So when I take the derivative, it's negative 1 x to the negative 2, which is equal to negative 1 over x squared. So that bottom derivative by itself is negative 1 over x squared. Now what? Flip it, right? A fraction, flip it. And so this really just becomes negative x, limit x goes to 0. I get the negative x squared on top over the x on the bottom. X squared over x is just x, right? Negative x here. Oh, I'm happy about this. Because now, let x go to 0. And what do you get? 0. The answer is 0. Now, does that mean that every single time that you have 0 times infinity, your answer is going to be 0? No. For this particular setup, that's the way it worked. But for a different problem, it might be something else. So you got to go through all the groundwork here and get it done. What you think? So we got 226. Okay. I think that's a good place. Anyone want to ask questions on the take-home quiz? Now's the time. Take-home, yeah. If you're happy, you can go. But I'm going to talk about the quiz for about 10 minutes. Let's make sure everybody's here today. Who's not here? Don't you think that what they should do is they should put like a sensor on the doors, and like when you register for school, they should like implant a chip into like the base of your skull, and then when you walk through, it's like, doot, you're here, and then when you leave, doot, and it's all, what? No? Yeah, like RFIDs, and just put them in your brain now. Yeah, you'd have to scan to get in, right? See, it's not, yeah, but I'm saying put it in the base of the stem of the, no? Okay, I can dream. It's going to happen one day. Okay, I'm just going to call your name, and you just tell me if you're here. Kevin, Aaron, Rodrigo, yes, Tyler, Lily, Brooke, Jorge, Alexis, Tamika's is not here. Where is he? All right, Kyle, Elizabeth, Paul, Sean, Aurora, no Aurora, Ernest, John Pena, Mark, Leon, Ruben, Jean-Luc, Anthony, Caroline, Mark, Mark V, no. Honors here, and Tim. All right. Okay, so what do you want to talk about? I can give you limited information, but I can give you information. Can you read the problem to me again, or tell me which one it is? Okay. Okay, so what's your question? I give you the height and the problem, right? At the instant in time? Yes. Okay. Yeah, you need to relook at. Let me see. Your cone looks like this, right? Is this your pile? And you're saying it's got a height, which you're calling h, right? And the base of this is the diameter. I'm just going to call it base, okay? And what's the relationship they're giving you? The height is always 1/4 of the base. That's what you said? So 4 times the height is equal to the base. All right, I'm just writing different ways you could write it. Now, what are you saying? Mm-hmm. Well, your R, though, your R is this, right? Well, I'll tell you this much. Your base is twice your R, or if you want, your R is half of your base. But you got to make all the things work out correctly. You're on the right track. Just you got to pay real careful attention to the way. This is the thing you do know. Your base is 4 times your height, right? You know your base is twice your radius. You know your radius is half your base. You know your height is 1/4 of your base. I mean, there's all these different ways you could write it. What you need to do, you're on the right track. You want to get rid of R, right? Yes, I agree. And you want to get it in terms of what? Height. Yes, that's the right way to go about it. But you got to make sure you get that conversion correct. Yeah. Then when you differentiate, all you'll have in there is the dV dt on one side, and dH dt will pop out on the other side, and that's all you need, right? Okay. Yeah. Just make sure you look at that equation again. Make sure you got all your conversion. Okay. Any other questions on the? I can take a look. I don't mind. I did them the other day also. Let's see. Let me do this. Can somebody hit the lights on their way out, please? There we go. Let's see here. It's a terrible glare. There we go. Am I still recording? I guess I should stop at some